Everyone thinks the power supply feeds the chip, but a GPU proves otherwise. It slams from idle to 1000 amps in 1 nanosecond, before the regulator millimeters away can even react. It is electrically too far. Here is the trap. The GPU core runs at roughly 1 volt. Let that rail sag even briefly below its floor and the logic corrupts. The chip glitches or crashes. And 1 volt is a tiny budget. A droop of just tens of millivolts eats a big slice of it. So this is the real problem. Nobody on Earth can shove 1000 amps through inches of copper in a single nanosecond. The supply simply cannot arrive in time. Start with why speed is the enemy. Push current through any wire and the wire fights sudden change. Every trace, every via, every tiny copper bridge behaves like a spring that resists being yanked. Engineers measure that stubbornness as inductance. Here is the rule that governs everything. The faster the current changes, the bigger the voltage it kicks back. Slam the change hard enough and the wire slaps back with a real voltage drop. Now feed in the numbers. A GPU changes its draw by 1000 amps in 1 nanosecond. That rate is brutal. Against it, even a whisker of inductance becomes a wall. That is just a few nanohenries buried in a trace or a via. Multiply that tiny inductance by that violent rate of change. You get a transient voltage drop big enough to blow through the 1 volt budget on its own. Picture it. The charge you need is sitting back at the regulator. But between there and the die lies inches of copper. Every inch adds inductance, another loop the current must fight through. So distance is not a minor detail. Distance is the enemy. The farther the charge has to travel, the more the path resists. The rail sags deeper before help arrives. But that raises the obvious question. If distance is the problem, why not just move the charge closer? So move the charge closer, but not with one hero part. The fix is a team of them, staged like fire buckets at different distances. A capacitor is just a device that holds charge and can dump it fast, because it sits pre-filled and ready. Engineers stack them in tiers, each one closer and quicker than the last. Farthest out near the regulator sit the big bulk capacitors. These are large reservoirs that hold a lot but respond slowly. In the middle, scattered across the board, sit smaller ceramic capacitors, the everyday workhorses of power delivery. And nearest of all, hugging the chip, sit the on-package capacitors. Here is the trick that makes the whole thing work. Each tier is tuned to a different slice of time. The bulk caps handle the slow stuff, the sags that last microseconds. The board caps cover the middle window, the tens of nanoseconds. And the on-package caps own the very first nanosecond, the instant nothing else can possibly reach. Why split the job like that? Because the same distance that makes the regulator too slow also makes the far capacitors too slow for the fastest events. A capacitor 2 inches away still has inches of inductance in front of it. So closeness is not a luxury here. It is the whole spec, which points straight at the fastest tier. What makes those on-package caps quick enough to catch a spike measured in a single nanosecond? Here is what makes them fast. On-package capacitors do not live out on the board at all. They sit on the same little slab the GPU is mounted on. The package, microns to millimeters from the die itself. That closeness is the entire point. Remember, the wire's resistance to sudden change grows with the length of the loop the current has to make. Shrink that loop to almost nothing, and you shrink the inductance to almost nothing with it. So the on-package cap barely fights the current at all. It can pour out charge in that first nanosecond, long before the board caps have even begun to respond. Those sit inches away with their longer loops. Now where does that charge come from? It is not magic. During the quiet moments when the GPU is coasting, the regulator calmly tops these tiny capacitors off, pre-charging them like buckets filled between fires. Then the workload fires. The die demands 1000 amps in a nanosecond, and the on-package caps, already full and sitting right there, simply let go. They release their stored charge on the spot. No travel time, no long copper road to cross. They do not wait for permission from the regulator. They do not ask the board. They just dump. But a capacitor is a small bucket. It empties fast. So catching the first instant only buys time. Which raises the last question. What happens in the microseconds after that first nanosecond, once the tiny cap runs dry? Now the whole machine clicks. That 1000 amp nanosecond spike is never served from far away. It is served locally, then backfilled by a relay. The on-package caps supply the very first instant, right at the die. A few nanoseconds later, the board caps take over and refill them. Microseconds after that, the bulk caps in the regulator restore the long-run average and top everyone back up. It is a relay race in charge. Each runner covers exactly the leg the next one is too slow to reach. And that reframes the whole paradox from the start. The regulator being too slow was never a flaw. It never had to be fast. It only had to keep the average steady over microseconds, a job it does perfectly. The speed was quietly handed to the last inch, to the tiny capacitors sitting right against the die. This staged handoff, first inch to board to regulator, is the real reason a modern GPU can hold near 1 volt rock steady. Its current lurches by 1000 amps in a single nanosecond. The supply never raced the spike. It just made sure something closer already had. So here is the one thing to carry away. Proximity beats power. In that first nanosecond, the closest charge wins. Not the biggest supply, just the nearest bucket. Next time, we open up the regulator itself and the microsecond tier of that relay. We will see how the board caps and the VRM refill the line and hand the baton back. Follow along and the whole power chain stops looking like magic.